first speaker. Our first speaker is Cory Mottice. He is a forecaster at the National Weather Service office in Cleveland, Ohio. Cory is a 2010 graduate of the University of Oklahoma and has been working in the National Weather Service since 2014. Please extend a warm welcome to Cory.
Good morning, everyone. Okay. All right, so this presentation was created by myself and two other forecasters, Zach Stefkovic, who'll be giving a talk later today, and Nick Greenewalt, which many of you here know. He gave a talk last year and went to the University of Oklahoma. So we're going to be talking about the tornado outbreak that occurred on November 5th of this last fall. And we had quite a few tornadoes across Ohio. It was a pretty unique event. As far as the magnitude of it and how many tornadoes we got. So it's kind of interesting. We're also going to look at the normalized rotation values in GR2 analysts. Did a little bit of research on that, something I've been looking at for a while. We kind of came up with some interesting numbers for that. So we'll get started. Alright, so a little bit of climatology for tornadoes in Ohio. So there's been 366 tornadoes throughout the state of Ohio since 2000. And there's kind of a breakdown there by the NWS office of how many tornado warnings or confirmed tornadoes have been through each CWA. So Wilmington has the most, 177, then Cleveland the second most. We have the two largest portions of Ohio, so it makes sense that we have the most. With fewer as you get to other CWAs that cover smaller and smaller portions. If we take a look at the breakdown of the monthly distribution of tornadoes in Ohio, see we kind of have two peaks. We got our spring and early summer, and then we have another late peak in November. So November tornadoes are not all that uncommon in Ohio, as this event will go to show. If we look at the hourly breakdown, you can see most of them happen in basically the 2 to 7 p.m. time frame, and this event, that's pretty much exactly when all the tornadoes occurred, from 2 to 7 p.m. So it fits right in line with what we're typically used to seeing. Here's just a quick look at the spatial distribution across Ohio. This is all tornadoes, including QLCS tornadoes and supercell tornadoes and other tornadoes since 2000. Kind of spread across the state, but you still see a maximum generally across the western area and parts of southern and southwestern Ohio. If you look at just the QLCS tornadoes, we have the maximum that kind of goes across the Cleveland CWA. A lot of that's because of this event that we just had here in November. So if you discount that, previously most of the QLCS tornadoes in the last 17 years have been across the western parts of the state, which makes sense. That's where you get more moisture usually, more instability during the day. By the time storms get to the east, it's generally later at night. All right, so on this day, November 5th, not May 5th. We had 14 confirmed tornadoes, a couple of which were EF2 tornadoes, a lot of EF1 tornadoes, and just 2 EF0 tornadoes. Of the 14 tornadoes that we had, 10 of them had a debris signature associated with them. And this appeared generally within a minute after touchdown. And part of the reason that we think that happened is because it was the fall, there's a lot of leaves on the trees, a lot of debris to be picked up, so radar was seeing that pretty readily, even for these weaker tornadoes. There was widespread significant wind damage across pretty much our entire CWA, so most of northern Ohio and into northwestern Pennsylvania, including most notably a macroburst that traveled about 100 miles or so, about 13 miles wide at its maximum, and we had a measured wind speed of up to 105 miles an hour with that. The storms overall were fairly shallow topped, only an average equitop height of about 29,000 feet with all these storms. I'm going to go through a quick rundown of the environment leading up to this event. So we're going to start out with the upper air analysis here. This is 12Z, so this is the morning of. We've got the trough coming in from the west. You can kind of see some, if you look at the 500 millibar chart, there's some little short waves embedded within there. And if you look at the 300 chart, you can see the purple lines up there. That's the upper level divergence. Already in the morning, we had quite a bit of upper level divergence with that jet that was the southern portion of the jet stream. We were in the left exit region of that. As we go through the afternoon, the jet gets a little bit closer, strengthens a little bit. We also have a second jet that's developing across portions of the lower and central Great Lakes. So what we end up having by the evening hours is we have a couple jets. So we're in the left exit region of the southern jet, and we're in the right entrance region of the northern jet. And that's co-located right over our CWA, Northern Ohio. And so as you can see by the mess of purple lines on there, that's all your upper level divergence, which is pretty much through the roof. And we still have plenty of moisture. If you look at the 850 and the 700, we have moisture streaming in with southwesterly winds, and pretty strong winds in general with about 40 to 60 knots through these layers. Going down to the surface, what we had was, we were in the warm sector. The warm front was north of Lake Erie. Cold front was off to our west. Throughout the day, we are going to be watching this cold front slowly push in to our area in northwestern Ohio. There were a few storms that were triggered by some lake breeze boundaries that we had, but the main forcing was going to be with this cold front as it came through. We have dew points in the lower to near mid-60s, with temperatures by the afternoon getting up into the lower 70s. So finally, by about 4 p.m. or so, we had the cold front starting to move into northwest Ohio. And that's when we started seeing the storms, some of the first severe thunderstorms move into our area. And by 0Z, the cold front's about halfway through Ohio there. By this time, most of the tornadoes were done. It had been raining widespread everywhere, so the instability went down to nothing. It was late at night in the fall. You don't have a lot of heating left over from the day to continue keep these storms going through the night. So if we look at the CAPE, this was generally a very high shear, low CAPE event. We had 500 to 1,000 joules per kilogram on average of CAPE, with the highest values being across the western part of our CWA. And since it was the afternoon, our surface base and our most unstable CAPE are pretty much the same, since the lower levels of the atmosphere were mixed out. And then by 21Z, here's about our peak instability. And as we get into 0Z, C gets pretty stable as the storms and the rain has overspread the entire area. Alright, so looking at the shear, this is what's kind of interesting with this event. With a lot of these high shear, low CAPE events, you have good values of shear, but you don't have ones that are quite as extreme as what we saw in this event. So in the morning, we're still looking around only 25 knots or so in the 0 to 1 kilometer shear, with 0 to 6 kilometer shear around 40 knots. But as we continue through the day, we're going to see the shear ramp up pretty significantly, especially in the lower kilometer. So here we have at 21Z, we've got around 40 knots or so of 0 to 1 kilometer shear. So we have a lot of shear present in the low levels of the atmosphere. And then by 0Z, it's starting to shift off to the southeast as the front has moved through. So with those values of shear, we also had an MCV move through, which we'll talk about. That all contributed to very high levels of storm relative velocity with this event. So as by the time the storms moved in here around 21Z, you can see the bullseye start showing up in the 0 to 3 kilometer storm relative velocity. And we had values of 500 to 800 meters squared per second squared storm relative velocity. So that was just absolutely through the roof with this event. Precipitable water, LCLs. The LCLs were extremely low, generally less than 500 meters, which is pretty typical for these fall events in Ohio. Precipitable water is around 1.3 inches, which is near the climatological maximum for that time of year. The sounding actually from Wilmington had 1.4 inches, so it may have been a touch higher than what this graphic shows. So there's a look at the Wilmington sounding. What you can take away from this is you can see, if you look at the wind profile on the right, we have our slightly backed winds at the surface, veering with height. Pretty significant speed shear we can see present there, and it's a pretty moist atmosphere overall, not much of an inversion in the lower levels. So this is the hodograph from that sounding. You see nice curvature, generally most of the shear confined to the lower 2.5 kilometers. Now this was a study that Paducah had done, and we just kind of wanted to compare our values that we had present for this day with what they found to be favorable for cool season QLCS tornadoes. So their values that they found favorable were the middle column there, and on the right is what we actually had present that day. So every single value far and away exceeded what was their base criteria for tornado development in the cool season weather. And as you can see, the shear kind of stands out pretty significantly in the low levels. All right, so this is a radar evolution of the entire event. So the front right now is out across central Indiana, and we have some thunderstorms that are going on across Ohio. A lot of that is just rain, but there are a few thunderstorms that were triggered by some lake breeze boundaries, which actually caused a couple of our tornadoes. There were some supercells in Indiana, and as they crossed the border into Ohio, these supercells kind of merged together, and we saw the squall line form and an MCV develop. And it's kind of hard to see here, but we'll take a closer look here as this moves through. Right about this time frame is when the strongest tornado occurred in far northeast Ohio, and then it moved out of the area and was over with. So if we take a closer look at that here, you can see some of the thunderstorms moving right along the lake shore there on the leading edge. Some of those are the ones that produced our first couple of tornadoes. Now, the supercells are beginning to merge as they're moving into Ohio, coming in across the southwestern portion of our county warning area there. And you can see at the northern portion, up around here, you can see an MCV that developed. You can see the dry slot kind of wrapping in with the precipitation there. And that was a key factor for producing a lot of these tornadoes and the wind damage, a significant swath of wind damage we saw with the macros that occurred as it moved through that area. So this is a map of the tornadoes that occurred that day. So we have the colors there denoting the strengths of them. The yellow ones are the EF2s. Now one thing that's kind of interesting is the two westernmost tornadoes were the first two tornadoes that occurred with this, and they were the strongest tornadoes. So what happened was, as the storm was moving through, we had the initial development of the MCV that developed in the dry air and the rear inflow jet wrapping in, and those produced the strongest tornadoes both on the southern line and the northern segment. And they were the first ones, and after that the tornadoes got progressively weaker. So these are the two that I was talking about that were produced by a lake breeze boundary. Not associated with the cold front at all. Very, very weak rotation. We're talking, I'll show an example here in a minute, but these had just a couple of pixels of rotation. Very difficult to detect on radar. The first thing that really triggered us to issue a tornado warning was seeing the CC get lowered significantly, picking up debris. One of I believe the easternmost tornado there had actually hit an apartment and ripped a bedroom out of it. So it's probably some of the insulation that got picked up into the storm that the radar is picking up on. So this southern middle cluster here, that was associated with the MCV as it was going through. That's generally the tornadoes that we saw with that. Now once you got east of there it was wind, but that was all associated with the MCV. And then the southern three were associated with the second Boeing index of this line of storms that went through, and they were basically all located right along or just north of the apex of that bow, as you would expect. Now in between where it looks like nothing happened, this is actually where we had a significant swath of wind damage across this area. This is where the macro burst occurred with 100+ mile-an-hour winds. We had widespread tree damage across this entire area. At the time, we were just getting phone calls, pretty typical that we get in Ohio with severe weather. Trees down, some power lines down. We didn't know how bad it was until after the fact, because a lot of this was all occurring after dark for the most part. The next tornado that occurred is this one up in Erie, Pennsylvania. Again, this was not associated with the cold front. This one was associated with the lake breeze boundary up there. And we'll talk a little bit more about that tornado here in a minute. And then the last one to occur was the strongest tornado of the event, which actually occurred as the MCV and the macro burst was continuing across the area, and as it was starting to dissipate. It was basically its final gust that it put out, and it produced the 7-mile-long EF2, strong EF2 tornado there. So we're going to take a look here just at a close-up of a few of these tornadoes. So this is the first tornado that occurred at the event. This is the Sandusky County tornado. This occurred along the lake breeze boundary, and you can see the rotation there in the top right with the velocity. It did have 47 knots of gate-to-gate shear, but it only lasted for one scan. It was there and it was gone. And you can see what it picked up on with the correlation coefficient there in the bottom left screen. And that image is 0.56 showing the debris signature there. And it was a rain-wrapped storms. You can tell in the top left image, which all of these were, even though this one was during the day, there's really no way that anyone is going to see this. And the normalized rotation, which I'll have in all of these graphics here, is the bottom right, and the value of that was 0.89. And we'll talk about the significance of that here in a little bit. All right, a little while later, now these are tornadoes that are associated with the front that came through. So here we're looking at around 5 p.m. in Huron County, and we have multiple tornadoes ongoing at once. So very weak shear with both of these. At the most, we have about 29 knots of gate-to-gate shear. Our CC with the southern one, we can see that it was picking up clearly debris. Now the northern one, it does look like there's some debris there, and there may be from this tornado. However, there was actually another tornado near Republic, which you can see there in the left center of the graphics. And it's kind of leftover debris from that tornado, so it was a pretty cluttered field. So it's hard to tell if there was any additional debris being picked up by this one. It was mostly over fields. It really didn't hit too much. So it kind of gets muddled in the mess there. And if you look at the normalized rotation values, again, we have 0.81 and we have 1.09 for that northern one. This is just the next scan. You see normalized rotations beginning to come down. The shear is about the same or weakening a little bit. Just goes to show you that most of these tornadoes, this is what they look like at best. It's just very weak rotation, did not last more than a couple of scans. And as you can see, based on the collocation there on the left, the top left image, where they're associated at with the radar, especially the northernmost one. It's not really in a very clear-cut area. If you're just looking at that on your radar, nothing's sticking out to you. And the southern one as well, it's just, they're rain-wrapped, they're quick spin-ups, little mesovortices within the squall lines that's moving through thanks to the MCV. So this was a lot of the type of damage that we would see with these tornadoes. Is generally a lot of farmlands, so there's a lot of tree damage or some kind of outbuildings or silos, something like that. That's what we are looking at to rate the storms. Now if we look at this one, this is one of the most impressive tornadoes as far as the debris signature goes. The velocity signature is pretty good in this one as well. It's around 81 knots for one scan. It did weaken pretty significantly after. The normalized rotation value is over a 1.2. And then if you look at the CC, what's really interesting about this is it was down to almost a 0.4, so very low. But the actual signature went up to 17,000 feet, which is extremely high for a weaker tornado. Generally, if you're seeing debris that high, it usually means it's a stronger tornado. But in this case, it hit a ton of trees that had a lot of leaves left on them. It hit some abandoned buildings down there that had all kinds of insulation and real light objects that could get lifted up. And the updraft is pretty strong with this storm, so that's kind of the thinking of why it was able to get so high. Because of how much it hit with all the loose debris and being the fall season. If this same tornado would have happened in the middle of summer or the dead of winter where there's no leaves in the trees, we wouldn't have seen anything like that. And in this tornado, we had talked to the farmer down there, and when we're going doing storm surveys, we're talking to people trying to get ideas for what they saw, what they heard. This particular farmer, it went right over his farm, and he was outside at the time. Trying to get some of his cattle in and his horses, and he actually said he witnessed a cow being picked up by the tornado, and it was thrown. And I thought that was really interesting. Actually, I might have some footage. Oh, yeah, here we go. So there's some cows. That was in Oklahoma, but all right. So now we're going to take a look at the macroburst here. So this, you can really see it stand out in the velocity image on the right-hand side. So just take a look at this coming across in the northern portion of Ohio there, and you can see those colors just light up. So radar, the base velocity was showing us that there were winds of over 100 miles an hour with this. We had warnings out, I believe, to 90 miles an hour at the time. And this produced a large swath of wind damage as it came across. Now it's pretty interesting, if you look at the reflectivity on the left-hand side, you'll notice that that dry swath coming in on the backside. That's your rear inflow jet. So those real strong winds are being mixed down to the surface. You're getting the evaporation, the precipitation back there. And right along the leading edge of that dry punch is where we saw a lot of those tornadoes. And that was the leading edge of this significant swath of wind damage that went pretty much this entire loop here from the start to the end. So that, it really stood out on radar. And at the end, if you're looking at far northeast Ohio here, up in this area, right in here, that's where the strongest tornado occurred. And you can see that it's pretty much right at the end as that macro burst is starting to kind of dissipate and fade out. That's where that tornado occurred. And here's a closer look at that. So there really was not a lot of signature at all. We had to look really hard to find something with this particular tornado. There's no debris indication, even though it was the strongest tornado there was. There's the bottom left there, we see no indication of the CC. It wasn't in a bad location on the reflectivity, but again, it had been producing just straight strong winds through this entire area. And the velocity was very broad, the rotation with it. It was 33 knots of gate-to-gate shear. If you get really specific and pick out some of those pixels, but I mean overall, it's very broad shear. And we're looking, keep in mind, we're pretty far away from the radar. So on this slice, we're looking up about 7,000 feet. So we're not seeing much of the lower part of the storm. Now, something that's kind of interesting with the normalized rotation, you'll notice the value is above a 0.8 again, and it's at 3 kilometers though. So it's not near the surface, it's not at the lowest tilt, it's up another tilt. The lowest tilt was only about 0.6 or so, but if you go up, you see a value of 0.8. And when I'm looking at normalized rotation, which I'll talk about a little bit more here, I like to look at the lowest 3 kilometers and kind of take the composite as the highest, and I'll tell you why here in a sec. So here's some of the damage from that tornado. It destroyed a couple of mobile homes, did a lot of damage. It was pretty impressive. And it was on the ground for almost 7 miles, about 200 yards wide, 127 mile an hour winds. You can see, especially in that right picture there, what it did to those trees. Now these trees did not have a lot of leaves on them, so it's not like it was in the summer where it has a lot more to work with the wind to twist it and tear it. These were, I'm sure they had some leaves left, but for the most part there wasn't too much left on it. Alright, so finally the Erie tornado and all the problems that we have in northwest Pennsylvania. So there's a tornado going on right now in this graphic. I don't know how you'd be able to pick it out from here, but if you can, I'm impressed, because maybe if you're looking at the CC, you look over the Middleborough area, maybe there's some kind of enhanced rotation there. You look at the velocity itself, it sure doesn't show you much of anything. Now we're about 100 miles away from the radar, so we're looking up almost 10,000 feet here. And at this time, there's a tornado occurring right at the center of that T. And this was the tornado that occurred in Erie that was not warned, because there's no way you would ever warn something like this. But we're looking up at 10,000 feet. These tornadoes, these were shallow storms, all the rotation. This was along the lake breeze boundary, so you're getting those localized spin-ups that you're not going to see the depth of that. These ones may have formed from the ground up as opposed to the top down. So it's very difficult with our radar being so far away. Buffalo's is a little bit closer, it's 92 miles away, but there's just as much problems with theirs as there is ours. So this was the damage out there, it was mostly tree damage. And a little while later, we had this signature show up on radar. Only about 20 minutes later. Tornado warning was issued for this storm. We still at this time did not know about the other tornado that occurred, which was pretty much consistent throughout this entire event. We did not find out about any of the damage until well after the fact, because it was at dark. All the reports we were getting were just your typical trees down, power lines down, nothing to indicate tornadoes in most areas. What we were basically relying on was the correlation coefficient and being able to see some of those debris signatures on radar, because we had no ground confirmation that tornadoes were occurring otherwise. And it's pretty good rotation around Girard. We have normalized rotation values over 1, and absolutely nothing occurred with this. What was kind of unique with this event is that at the time there had been a lot of rain in the day over northwest Pennsylvania, So there was a flash flood warning in effect. They were getting flooding in the Erie area. Well, one particular house, there were 2 occupants in it, and this tornado warning was issued. At the time, they were upstairs because the flash flood warning was issued. And then the tornado warning was issued. So what do? Well, they went down into their basement, and against all odds, the flash flood collapsed their basement wall, and they both drowned in the basement. And yeah, as meteorologists, that's the last thing we want to happen. And it's competing warnings. One tells you to go high, one tells you to go low. What do? I mean, one's more imminent than the other, but there's really no way of knowing exactly which one that is. And most of the time, the tornado is going to be your more imminent one. And it wasn't like it was in a super hilly area or anything. The water is just kind of pulling in from the road. So that was, it's a challenge that we don't often think of, but it's one that's out there. So as I was talking about in Erie, there's kind of some of the stats on it of why it's so difficult with the radar to see what's going on out there. Outside of Erie itself, there's not a lot of population in Northwest Pennsylvania, so a lot of the reports we aren't going to get anyway. It's mostly trees and forests and hills out there, unless you're within the populated areas around the lakeshore. But outside of that, we don't get many reports, real-time reports. So during this actual event, how we did it as an office, we had plenty of staffing. We had a lot of people in the office. We had every single computer being used. We had 3 people answering the phones, but the problem was we were getting a lot of phone calls. They were all pretty much telling us the same thing though: trees down, power lines down, 0 reports maybe 1 report in Sandusky County of a tornado. I think that was the first one that we got. The other ones were all coming in well after the fact. And so what we're trying to do at our spotter talks this year and is making sure that people, if it's nothing imminent, life-threatening, try to get that information to us through our social media channels. Because we're handling so many phone calls as it is, and we have 3 people doing it and we can't keep up with it. We want to be able to have the phone lines open for something that's imminent, life-threatening, significant damage, whatever it might be. So it made it pretty difficult when we have that high volume of calls coming in, even with the full staff. I think we had 9 people in the office. So warning strategy, we had 2 warning forecasters for about half the event and then 3 for the second half of the event. So there are plenty of people on radar. We had an event coordinator, and it's key in environments like this where we're not necessarily getting the reports that we're expecting to be getting, that we have a meso-analysis present going over the current conditions, looking at the SPC meso-analysis page, looking at other factors, current observations, whatever it might be, to pass that along to the warning forecasters so we have an idea how the event's evolving, how the atmosphere is evolving. Is the shear instability increasing, decreasing, what's going on? So that's key to have in any event like this, and it becomes extremely useful. All right, so the last thing I want to talk about is normalized rotation. So for those of you who do not know what normalized rotation is, it's a product within GR2 Analyst. It essentially computes the azimuthal shear and puts it into values and terms that are kind of easy to interpret and understand. And what's nice about this is it does account for beam broadening. The farther away you get from the radar, the bigger the bigger grids that you have, so the data is not quite as good, it's more sparse. It doesn't try to account for that, and it gives us a pretty good indicator of rotation in the storms. So the motivation behind this is most of the weak tornadoes make up most of the tornadoes that we see in the US. About 77% of all tornadoes are EF0s or EF1s. And these tornadoes are notoriously hard to predict, they're hard to forecast, they don't show up very well on radar a lot of times, they're very short-lived, and all of that leads to minimal lead time. And our goal is to try to improve the lead time of tornado warnings, and it's hard to do when you have so many weak, low-end tornadoes occur. So what I wanted to do is I wanted to assess the normalized rotation parameter and see how that could potentially aid a forecaster in issuing tornado warnings for these weaker QLCS type tornadoes. So the goal is to determine if there's any values that were associated with tornado genesis or leading up to the time of a tornado to try and get lead time on it. Is there a trend in the normalized rotation value that could be useful? All right, so this is a little bit of how I went about doing it. It's completely subjective with how I did it. Now, I only did it at this much detail for this one event for now. So I went through every value of the normalized rotation, but I only used the ones that were more discrete in nature. And I'll show you an example of that, what I mean here in just a minute. And to make sure I'm not using any bad data, I made sure that the normalized rotation values matched up with some sort of velocity signature, since that's generally what you're going to be looking at first to get an idea, make sure something's not out to lunch and just showing up on whether you have windmills or something like that that's giving you bad data. So I didn't use any of the values that were linear in nature along a squall line, for instance, which I'll show you here in just a sec. I did not use data beyond 80 nautical miles from the radar because once you get past that point, the data seemed pretty useless. It was all over the place. So that's just kind of a generic value I picked, but generally speaking, beyond that data, it's pretty degraded data, but beyond that distance. And the other thing that's more unique to our area is I did not use any of the values the storms that started over the water or that were only over the water, because we have no way of knowing if it produced a water spout over water before it moved on shore or anything like that. So I didn't use that data just because we have no way of verifying it one way or the other. Alright, so here is just an example picture of, this is from that event, what normalized rotation looked like and some of the values that I would choose and did not choose. So all the ones in yellow are what I mean by more discrete in nature. They're separated, they're kind of circular in nature, and you have your linear line along the squall line, which that was elevated the entire way through, well over like 0.8 to 1. So that's not going to be too useful. So I went and I picked out every other discrete value. And I did the composite like I was talking about earlier. So I went through 0 to 3 kilometers, so up to about 10,000 feet, and that could mean more than 2 to 4 scans, depending on how close or far away it was from the radar, 1 to 4 scans. So I used the composite, meaning I used the highest value that I found throughout that layer when I was doing this. All right, so for every instance of one of those discrete normalized rotation values that I found, I would use that and see, did it lead to a tornado within 10 minutes? I want to do a 10-minute lead time since these are weak tornadoes, short-lived. You're going to be lucky to get 10 minutes of lead time on anything like this, so I didn't want to go any more than that. If it did produce, it counted as a hit. If it didn't, counted as a miss. And this is what came out of this event. This is your box and whiskers plot. And you can see a general increasing trend with lead time there in the bottom. So 10 minutes lead time, 5 minutes, 2 minutes, and as touchdown. And we have a general increasing trend, but it's kind of hard to view data like this in this particular event to find it too useful. So there's better ways you can look at this. So this is the percentiles. So for instance, if you wanted to capture 95% of all tornadoes with 10 minutes of lead time, you'd have to use that 5th percentile line there, which is a value around 0.4. But if you use that, of course, you can assume your false alarm ratio is going to be through the roof. So I wanted to then go and figure out what is the false alarm ratio using these values. So here's the table of that chart that you saw. These are the numbers actually broken down. And what I did based on those hits and misses, I went through and I just calculated the false alarm ratio. And you can see the false alarm ratio decreases pretty significantly as you get higher and higher value. And this is just an example here of how you would use that as an interpretation. So on the left is that chart. If we wanted to capture 50% of the tornadoes with a 10-minute lead time, we'd use that value of 0.5 something. And you look over on the right, figure out that false alarm ratio is 65%. If you want to capture it with 5 minutes of lead time, that's going to reduce your false alarm ratio to 38%. So a pretty significant decrease as you go up. And this is an example of the false alarm ratio decreasing. Now it kinks up at 1, but this is just one event. We only had a couple of events with over a 1 in this particular day. So those are your values. Generally what we found to use above 0.5 to 0.6, start paying attention. Once you get above 0.6 to 0.7, there's a chance, a pretty good chance that you have decent rotation could lead to a tornado within the next few minutes. And above a 0.8, tornado is possible at any time. Now, this is just one event. So what's next is essentially expanding this to multiple data sets throughout. I generally want to stick with QLCS tornadoes with this, the weaker ones, in the cool season. Maybe we can break it apart, cool season, warm season, and see if these values hold up through 100, 200 other cases that happen. So that's some research that we'll continue doing and seeing how that all pans out. That's all I have. So,
We just have a few minutes for questions, about 5 minutes or so for questions.